what is information? It's red. Now it's green. Good. So what is information? How would we define information? Right? And because there are many ways to define it, and it really depends on your perspective, but we really want to count. Okay? So as I say, this course, in terms of mental procedure, is about two things: flowing and counting. Well, counting and classifying. Actually, combinatorics is a little bit, it's not accounting, right, only. It's just counting and classifying. Like we say, N1 in this region, N2 in this region. Okay? And so, surprisingly, it took a relatively long time to define quantity on which most people agreed eventually. And let's say I have 1, 2, n boxes, and somewhere is a candy. And and somebody tells me the candy is in a box number J. How much information I received? Okay? So I knew that there was a candy. Now I know in which box it is. So I want to define some quantity I, which can only depend on the number of boxes n, right? When n is 1, it must be 0, right? This is the first condition. I of 1 is 0. If there is only one box, I don't need any information. Okay? Now you can say that my information is determined by what I get. And I got candy, and no matter what is the number of boxes, I get the same single candy. So my information must be one candy and not anything which is independent, right? And this is a legitimate definition, just not what I want. I want somehow to be this message which brings it to have it measure related to the degree of uncertainty that I had before and which this message eliminated. So this is a general idea. It's the most important idea of all this science called information theory, which surprisingly in a moment will be related to all statistical physics and entropy. So information will be measured by the degree of uncertainty which was eliminated by this information. In this sense, we expect it to be monotonic function of n. Okay? We expect it to be monotonically growing function of n. The more the number of boxes, the more was indeterminacy before, and it's okay that I start from 0. It's good. It must be positive. When I get this information, nothing is distracted from me. Right? So now, what kind of, there are many monotonic functions of n, but I really want it to be a kind of additive if I really can classify my problem as hierarchical. For example, I can inside every box have compartments. Let's say m compartments. And I'm actually interested in which compartment is my candy. Okay? So generally, I would have n compartments. At every box, there is m compartments. So if I'm interested in I of mn, information in which compartment is a candy, I'm saying, tell me first in which box, and then tell me in which compartment is in this box, right? I would generally prefer to stop here, even though it's a beautiful branch of mathematics, of which is just, you know, a zeros page. So of course it's a logarithm, right? That's it. End of story. And now there are different logarithms, as you know, and we'll be mostly working with logarithm 2. And it's because we like our measure to be number of questions, and we want our questions to be childish. Yes, no, black, white. Okay, so this means that we want our questions to be binary. So it's only two outcomes of it, 0 or 1, or yes, no. And then the units in which this is measured is, of course, we'll measure in binary digits, which for simplicity we call bits. As I probably told you in the first lecture, I don't remember, most of the discoveries in physics was done by PhD students, at least in the last 200 years. So this was a PhD student at Berlin University who did not really like his PhD subject of research. It was Leo Szilard, a young Hungarian, and Max von Laue, who was a big Nobel laureate and all this, and he gave him a problem which he intensely disliked. So Leo thought about something else, and then he met some younger professor, not that important, with whom he was not afraid to talk, called Albert Einstein, and told him that, you know, I have this idea, would it be feasible if I would rather write something about this and it would count as my PhD, than not what von Laue. And Einstein, and it was in the corridor, the building still stands, and Einstein listened for a few minutes and was visibly unhappy, and after 10 minutes he said, yes, write it down. You know, you all, some of you PhD students, it took 3 years to write it down because he was doing many different things. But in particular, this is where this word first appeared. This was the beginning of information theory, the way, and it was, but it has actually written in 27. And so that's the story. And it was about the number of yes-no questions. So essentially, we may say how we would find the box. We first ask right or left. We say left, okay, good. Now we ask right or left. Will be second question. Then the number of questions which eventually get our box would be logarithmic. Okay. Now, but if I would get a message, a set of letters, right? I don't know. Somebody sends me this. And again, I don't want to focus on, whether I am romantically involved. No, I want to ask how much questions needed to get this, right? What is the indeterminacy, not my emotional indeterminacy, but linguistic indeterminacy that were removed? So how I turn counting information here to here? What is this? It's a letter. Choice out of how many? 26. Well, if without a space, 26. Okay. Sometimes you make 26 plus space plus 5 symbols, and you get 32, which is nice because it's 5 bits. Anyway, you say there could be anything like what I'm saying. I had from A to Z, and I choose L. Good. Then I had from A to Z, and I choose O. Then again, I choose V, and then I choose E. So what essentially I did 4 log 226, which is, this is about 0.7 per letter. Okay, that's being consistent means stupid. You can get the information out of any set of letters, right? But of course, there is something about letters that, for example, if I would know that this is a 4-letter word, I actually don't need this because there is no other 4-letter English word which starts from L-O-V, right? And there are some other things which, so now I'm starting to say, wait, but there is something which is, I actually know. In this case, I didn't know anything except that there is a candy, which is already something. Okay, I get this assuming that I know that there is a candy. Now I know a lot of things about my letters. is that I really obtaining letters and not stones or whatever. And in particularly, I know that these letters are with very different frequencies. So some letters are more expected, like E, which gets, I don't know, what, 15% probably of any English text, except it's not in theoretical physics. There are other symbols more frequent, like QED or I don't know. But so I want to incorporate this. So for example, I do know frequencies, PIs or probabilities, and I run from 1 to 26. So how now I can quantify the amount of information brought by any message, or how much uncertainty is removed. Now I need to do it, and this is a very important step, which was done pretty soon after Leo by several people, Fisher, but Shannon was the main guy. I need to do it probabilistically now, because now if I really want to incorporate probabilistic information into counting how much information I get out of a letter, I need to really take something like averaging. Then what it would mean technically? So you want to really measure in some way how much information on average per letter. If there would be no other information per letter, you would get log 26, right? Now you say, yeah, but if I incorporate this, somehow this information must be more or less which I get out of every letter. So this I did not know probabilities. Now I do know probabilities. Now what every letter on average would bring me more information or less? Less. Why? Because I already know something. Yeah? My indeterminacy is less. The information that I obtain is how much indeterminacy is removed by bringing it. I now have less indeterminacy because I already know some extra. Remember this. Every time we add something extra we know, we lower possible indeterminacy, we lower information which it removes. Good. So now I need to do something like this. I take a big, I don't know, Oxford or Webster dictionary or whatever, or just open any, and just look at a very, very long string of letters, right? Good. I took it. It's something like I1, IK, IN. It's a very long string of letters. I get this long string of letters. I need to compute how much indeterminacy removed by obtaining this big string, it's a really long string, divided by n, it will be per letter information, average, right? What do I know about this string? It's behind me on the blackboard.
I mean, it's got length n, it's got, I don't know, entries in our alphabet.
Yeah. I know this. It means that I know that in this string, there will be P1 times letter A, right? It will be P2 times letter B. I know it, okay? Which means that because it's already a long sequence, and I assume that it's typical, we return over and over what is this typical. This is the idea. I know how many letters A, B, C, E in this. So the message does not bring me this information. I already know this. What it brings me, what I did not know пока I got this string. Order. Okay? So what I need now to count is how many orders in which I can take P1, sorry, P1 times n letters A, P2 times n letters B, etc. out of letter n. This would be a total number of orders, and any particular string removes this uncertainty. So I need to take this number of orders take logarithm of it, and that would be information. So how many orders? Question?
But you also have information about pairs and
About what?
about pairs and triples. You know how many times.
Wait, you have, I did not, okay? So far I have only, we are moving step by step from Boltzmann to Gibbs. We are now moving from Boltzmann to Gibbs. I really want you to know where on the mental map we are. Here we have no information except that there are 26 letters. Our information which brought by any letter is log 226. Good. Now we know that there are 26 letters, but there is a set of 26 numbers, pi's, sum of which are unity. We know these numbers. Okay? So now we ask how much information we get per letter, and we say, okay, compute how many different ways to put this P1 and P2 into this string and take a log of it. Good, so I'll take n factorial, divided it by n1 P factorial by n2 P factorial. I promised you combinatorics. Here is your combinatorics. np26 factorials. All right? Take logarithm, and that's it. End of story. So we all know Stirling formula, I guess, right? So it will be, and of course, I'm assuming that n is large. We already assume it, which means that I need n large to use this number of letters. So what, as a result, I will get? I would get the following formula. Well, we all know Stirling formula, right? So logarithm of any factorial is n log n. Okay. So what I'll get? I will get minus n sum over I from 1 to 26 or to whatever is I have pi log pi. Well, if I really use, this would be, and k is 1 over log 2. So that's the answer. So I use binomial nominal distribution, took a logarithm of it, I get this. Now I want this is the information brought by n string. Okay? And I divide it by n, and I would get information minus sum, and if I wanted it bits, pi log 2 pi, which is Gibbs entropy. Right? You see? So this is essentially, and you see the simple logic which appears out of it. Let's push this logic a little bit more. On a tutorial, you would have large deviation and a more kind of a general framework, but I really now want you to see some, which is a simple mathematical trick which used over and over and over in all these sciences, and it has different names, but it's essentially idea that if you add many independent random numbers, something simple and universal appears. It's unbelievably simple and very powerful idea. And there are a lot of very complicated mathematics, which is very scary in its terminology, but at the heart of it, it has this simple statement. Okay? So what happens is that if you add many, many random numbers, no matter what are their statistics, something appears. If you're interested, let's say you have your numbers, how I would call it, I don't know, y's, I call it y's. So if your x is the sum of yi from 1 to n, and you ask what is the probability of x, then of course the larger is this n, this probability looks very, very special. So for example, it may look like this is p of x for n1. But if you increase n, it would look like z. This is n2. And if you further increase it, it would look even, which means that, and there are 3 concentric statements, which I'm not going to now use. You'll talk about it in tutorials. First of all is the statement that this quantity very fast, exponentially fast, approaches its mean value. Because you sum numbers, right? So what you essentially would get as n grows, that x would be very close to its mean value. It's getting sharper and sharper. This is a simple form of it, which I'll be using now. It's called law of large numbers. Then there is a central limit theorem, which tells you that, and if you're interested in the probability around this maximum, it's getting more and more described by quadratic because it's a very sharp function, which means that locally it's a Gaussian distribution. It's called central deviation. It's called a central limit theorem, and there is even more powerful statement which says that the whole function could be actually have a form as exponent something minus n x over n, and it's called large deviation, h, and h. And this function is quadratic near maximum, but you can tell a lot about it even away from maximum, okay? So I just want to see this mental picture. But now I'm using a simple form of it, which is the law of large number, namely that if you sum independent random numbers, then you would get an exponentially fast approach to mean value. So now I want to use it to ask you the following question. Returning to this wise, to my letters. So I have A, B, A, C, D, Z. I have a string, okay? Let's say this is I1, this is I3. So you are given a string of letters. And I want you to answer how probable it is. A given string, one string. Only thing you know, like we assumed here, that it's a string of independent letters. It's not a Shakespeare. Shakespeare did not put one by one independent letters. So you have a set of independent symbols, object, macromolecules, whatever, right? And the question is how probable it is. Look idiotic, right? Kind of self-referential. How I can say how probable it is if I've never seen other sequences. But you know that they're independent. So how would you answer it?
We know the number of possible sequences. We just calculated.
We, at this moment, have only one sequence, very long, but nothing else. And I want you to look in at it. It's a blatantly self-referential question. There is no ensemble here, okay? And I want you to answer the question how actually probable it is. And I gave you a hint that the method by answering it is summing random numbers, independent random numbers. Now you know what is independent here, is that the symbols are chosen independently, okay? So what are must be random numbers that I sum? Let's meditate here. It's useful. So I'm trying to obtain probability distribution of a set okay. I'm saying that these symbols, they are chosen out of my alphabet or whatever. They're independent. What it tells me about the probabilities of different symbols? Yes?
They should just multiply.
Yes, the probabilities are multiplied. But I want to sum. How I turn product into a sum? Logarithm. You know, the guy who invented logarithm, he had this great slogan. Summing is easier than multiplying, right? These huge tables that they use, it immediately. So what I'm saying, let's consider logarithm of it, right? And how you know it, right? And this will be, of course, and let's divide it by n, so that I would, and let's take a minus for the heck of it. So what I would be 1 minus n, the sum of a logarithm of p of yi's, okay? So what I'm saying is that if I'm interested in the logarithm of probability of a big sequence, it's a sum of logarithms of it. And if this number is large, then it just can be taken as its mean value. Okay? And what is its mean value? It's a sum over all y. It's p. It's the entropy of the distribution y, whatever it is. But I don't know it. Or I do. So at the moment I obtain the formula. Look, I obtain minus 1 over n logarithm p is equal to s of y, which means that p is exponent minus n s of y. Excellent. Do I know s of y now, looking at this sequence? It's a very long sequence of independently chosen symbols. Huh?
It's that quantity which we calculate. So we know the entropy of a very long sequence.
How we know entropy of a very long sequence? I'm given one sequence, very long. How? But I know that they're independent symbols. How I get entropy? Huh? You just count, of course. You look at this sequence and you assume that it is typical. Namely, that how many times letter A would be in this sequence is probability of letter A. What is the probability of letter B? Let's just look at this sequence. It's long, right? So it's already representative. So again, and this is, I would not say the only piece of mathematics for information theory. There is a lot of bells and whistles added to it. But this is the main idea. It's called asymptotic equipartition. And of course, all the thermodynamics we can recast in this just terminology. I'm not sure, I don't think it's very good terminology, but this terminology. Now, it has much better name, which I prefer. It tells you the probability of a given sequence, a single sequence, when it's long, does not depend on this form of the sequence. It's just this. Okay? So another name for this statement which I prefer is the following. All events are almost equally probable. Okay? If sequence is long, it's as probable as other typical sequence. This probability goes down exponentially with length. Of course, the longer the sequence is less probable because it's out of many numbers. Or you can say that the number of all sequences grows like E and S. And S is the rate of this growth, which is precisely what we obtained here. Right? This is the rate with which, this is the number of all possible sequences. This is the logarithm of it, which means that the number growing as exponent, or as 2 if you want your entropy in bits, it will be 2 in the power n times your entropy. Okay? So this is really simple stuff. What it tells you that why entropy plays such an important role, it's a logarithm of probability. And when you have independent events, you like summing system. Then logarithms are summed. Okay? Probabilities multiply. Question?
So if I go back to my question, we know that there are words or specific, then if the length of the word is short compared to this long sequence, I don't care about the fact that...
A lot. That's the next chapter. We'll come to it. So far, we're just working with this object, right? So what I'm now doing, I'm making you see Boltzmann and Gibbs entropy is in a new light. Okay? So what is now Gibbs entropy is a rate with which grows the number of typical sequences made out of an alphabet with that probability distribution, with that frequency distribution. Right? Okay. Sometimes people are uneasy saying, so why the hell is a probability? There is nothing stochastic about it, etc. So in principle, one can tell all this story. Let me find where I did it, using my favorite language of compartments, which is not exactly, but imagine that, again, what I'm now trying to return to this and say how I can get this without all this stochasticity, randomness, and just assuming the same picture. Actually, I have it here. But now what I will do, I would have M different. So let's say I have M1 compartments in box 1, M2 compartments in box 2, MK compartments in box K. Okay? And again, I want to now define what somebody tells me in which compartment is my candy. Right? That would be an information which, and let me call M sum over J from 1 to N of Mi. So it's a total number of compartments. In the previous case, it was just Mn. But now it's a sum of Mi. Okay? So I would say that if I have I of M, the information, right? And it's an information of a specific compartment. I can say again that this is an information of a specific box, right? And plus the information about the compartment inside the box, right? So in a box I have Mi compartments, so I need to choose this. So I take this logarithm Mi, okay? But I would need to sum it over all i's, and each one with its own share of Mi divided by M. So in a sense, I'm now do a little generalization of that formula, which at this form kind of look trivial. So yes, if I want to know in which compartment, that would be information about box, and then information about compartment. Well, let me now turn the tables. So I say that, is it visible here, or you want me to go higher from back there? Okay, let me write it here. Okay. So now what I'm saying, that instead of looking at it in this trivial form, I want to look at it as a difference. So I'm asking again, what is the information, amount of information that I obtain about a box? Because it's like what we say, what is the mean information per letter? Now I'm asking, what is the mean information per box? Of course, there are kind of compartments inside the box. So what I need to do, I need to write is a log of M, which is the sum of M eta, okay, minus sum over I, Mi over M, logarithm Mi. So I can say that this is minus sum So essentially, what I just say is that this difference could be written as this formula. Now, if you call this Pi, it would be sum of but you don't need statistical interpretation of it, right? If you like it in purely combinatorial form, that this is just the statement that Gibbs entropy, again, would be a mean information of choosing a box. And now your probability just tells you how many compartments in a box. And again, you mentally assume here that you choose compartments uniformly. Okay? Now, all this is true, but a little bit kind of a physicist way. So just to feel us all less smug, I want to tell you how really, if you're a mathematician, how you go about defining this object. Because I already defined it. I got log, and then when I get compartments or when I get probabilities, I get Gibbs. And because we grew up with Gibbs, so we are not surprised. But mathematicians do it more accurately, yes.
So for the last line, why did you weight each log mi with mi?
Because
The physical interpretation.
Because in a sense, that's how many times I would actually use it. You see, for every box, I would use it differently depending on how many compartments are inside the box. So if there were no compartment in the box at all, just empty box by definition, then it would not be in this sum, right? So it needs to be proportional to mi, okay? Good. Now, what I really want you to give it a little bit more formally, okay? Which is that this formula appears like this. So what mathematicians say, that we're looking for some function. It's rather functional. So S is kind of functional of pi's. So there is a vector. I have a vector of numbers, the sum of unity, but set of numbers, and how S of p must be defined. That first of all, they say it must be continuous. Second, must be symmetric. Symmetric with respect to all these permutations. And most interesting, satisfies induction. And induction is like this. So if you have S of P1, P2, Pn, it must be exactly equal to S of one less variables. You see, I made a sum here, okay, plus and here I do the following things. So, in a sense, what is done here is considering a subdivision. So we kind of obtain first information whether any of 1 or 2. So we treat 1 and 2 as a single event, right? And this event has this probability, right? So in a sense, this is an information needed to consider the situation where 1 and 2 treated as a single event. And the rest is essentially, now if inside 1, 2, I want to choose 1 or 2. Then 1 would have this probability and 2 have this probability, right? So now I treat it as it happens, right? So this is induction. And there is a beautiful mathematics. And of course, you are welcome to try your own hand just to proving that this solves these three, yes.
I guess it makes sense that I, as this sum of probability weighted logs, does satisfy that. Is it provable that it's the only function that satisfies that?
Yes, that's the beauty of it. Well, up to rescaling or whatever. But essentially, this is only. But what I'm saying is that it's really, it's a lot of it physically is very intuitive, again, because we grew up with Boltzmann and Gibbs, right? And that's why I wanted to remind you all this so that it would be just. But the mathematics is, and a really good book, which if you'll be interested in more detail, is Cover Thomas. It's called Information Theory. It is that thick. It's full of theorems, and they are pretty transparent. I mean, it's kind of, yes.
Do we also require that, for instance, S of like a single
I guess it must follow already here, because it depends on how you properly, no, this properly induction. Yeah, for any induction, you need to give a first point. You need to start induction from somewhere, so you assume that S of 1 is 0, or I of 1. It's actually S because it's entropy, but it's just the same as I. So from now on, I will be often interchangeably use I or S, but at the moment, it's just the same. And the point is that it is sum of P log P, okay? So you now see different ways as it appear. First, it appeared out of Gibbs distribution when we considered subsystem out of microcanonical. Then it appeared just because we asked what is the number of typical sequences having these probabilities of letters inside of them. And then it appeared out of this pretty formal problem. Okay, good. Now let's study it, because now we have a really well-defined subject. We understand what is here. In a moment, we'll come to communication theory and we'll ask about more complicated things, how it's really they are correlated with each other. But for now on, we really, well, I still back to S. I'm a physicist, so I'm kind of, I won't pretend that it's not entropy. And you know, Shannon actually hesitated. Shannon asked for Neumann, who was a great mathematician. And for Neumann, there's this famous statement with people still, he say, call it entropy because nobody knows what it is, and you'll always have an advantage of using terms that nobody else understands, which was 40s, right? It was a very, historically, it was unbelievably interesting because von Neumann was, by the way, a very close friend of Leo Szilard, and von Neumann just came to Princeton before the war. He was very, like Einstein. He knew that the war will be like 10 years before, so he came to Princeton, and Turing came visited him. He actually very much wanted Turing to be at Princeton, and then Shannon was a young student at MIT, and then at the late 30s also met von Neumann, and then war started, and Shannon was in coding department, and Turing, as you probably know, was in decoding department. He actually solved problem of Enigma. So they brought several times Turing to, it's actually in New York, this building, I guess, is still, or maybe Hudson Yards demolished. It's near Hudson, this old building of AT&T, and they were forbidden to talk, they met, Shannon and Turing, so they were forbidden to talk about their professional work because they were from different departments, right? One was coding, another was, so they would talk about general things. And out of this, many things happened, and particularly what we're looking at, 1948, immediately after the war, they all did all these unbelievable things which kind of changed the way we look at all these things. Okay, good. So now let's study a little bit formal properties of such a function. I mean, I'm talking this function, right? Which also S of P. So first of all, it's a very simple statement that if you take S of P1, Pn, it is less or equal as S1 over n, 1 over n. Okay? And this property called, there are like 3 magic words which I use 15 times at every lecture, and this is one of them. It's called convexity. Is it clear why it's called convexity? Okay, let's say I have 2 possibilities. This is what essentially what is written here, and then generalization. Okay, if it's not immediately clear, we'll work on it now. Good. So let me really show you how this, of course, yeah, but just the fact that the function, let me erase it, x log x is a convex function, concave, or none of it. Minus p log p as a function of p. How it looks like. Just consider this function. And p from 0 to 1, right? When p is 0, it's 0, right? When p is 1, it's 0, right? Positive or negative? That's it. End of story. Well, you can check that the second derivative. Let's compute second derivative. So the first derivative would be minus log p minus 1. What is the second derivative? Second derivative is minus 1 over p. It's strictly negative. Right? So of course it's a concave function, right? And of course, when we sum such things, they would kind of, their convexity would be built on the convexity of this simple function. But let's now prove couple. First of all, those of you who would do homework would need it for homework. So let's show a few things related to this convexity. Moreover, that it's a huge industry, now multi-billion, probably trillion dollar industry, which exploits this convexity in all creative ways. Okay, so what we are saying now is that if I take, so let me call this S of p, small s, right? Okay. So let's say that if I take sum from I to n divided by n, S of pi's less than S of 1 over n sum of pi's. This is essentially what is written here. Because the sum of pi's is unity, if I treat this as probability. But this is a general definition of convexity. Multi-point convexity. Okay? And which means that what I did, I take functions of these arguments, took an average between them. Namely, I take, let's say, P1 and P2. Okay? These 2 points. Now, I took S of P1, it is this point. I took S of P2, it is that point. Sum them and divided by 2. Namely, I took this value, right? Now, what is on the right? I took P1 plus P2 over 2, it is this point, and took S over here. And it's always higher. Okay, that's convexity, right? So if whatever curve you have, you make a straight line, and of course you can make not 2 points, you can make 5 points and compute average between them. But you'll be always doing straight lines, which will be below your concave curve. Okay, that's the meaning of it. And now let me formulate this. So essentially is now that I do S of P1, Pn, n is small, n capital would be for the length of the message. It's a sum of E1 to n S of Pi's. By definition, yeah, where is my Gibbs formula? S is sum minus Pi log Pi equal to sum of S of Pi's. Okay? So I am saying that this is my this, and this is less or equal than n S1 over n, which is this. Sum of Pi's is unity, and this is S of 1 over n, 1 over n. So what I did, I proved you this based on an elementary property of this function. Okay? That's so out of convexity minus x log x, I proved your so-called, it's called entropy inequality. Okay? Now you can also do it a little bit more general, which is called Jensen inequality. This is probably what will, I'll probably have more time. Let's see. Good. So now we can also make it a little bit more general. Nobody say that I really need, when I'm taking these 2 points, to consider this point. I may consider this point, right? So I kind of mixed this value and that value in any linear combination, right? So I can take, for example, not them with equal weights 1/2. I can take one with the weight lambda and another with the weight 1 minus lambda. That will still be true. If I take it here, it still will be smaller than here. So now let me do a little generalization of this convexity. S of lambda A plus B 1 minus lambda. So I'm taking A and B, 2 arguments, and mixing them with a weight that sum to. And so what I claim that this is larger or equal than lambda S of A plus 1 over lambda S of B. Just a slight generalization. So this was lambda equal 1/2 for n equal to 2, and this is over here, right? Now what I want to do, I want to write the induction. So let me now take lambda equal, yeah, okay. Yeah, well, first of all, I need to formulate what I want to prove. I want to prove a general Jensen inequality, which is the following. Yeah, I have it over here, just this one. Okay. So now I want to prove this. We did it in a very particular case when all this was the same. Now I want to prove this for arbitrary n using induction, and I would use this induction in the following form. I would choose lambda equal to n minus n in this relation. A is equal to 1 minus n minus 1 sum till n minus 1 of pi's, and my B would be Pn. So what I would do, I would prove this relation. This is sum over n, this is sum over n. Just splitting it into 2 parts, n minus 1 and Pn, and using this formula, but now with weights lambda 1 minus lambda, and my lambda will be their relative weights, n minus 1 and 1, n minus 1 over n and 1 over n. Okay, so now what I will get, this one, I would get S 1 over n sum till to n pi's equal to, let me write it as a sum n minus 1 over n. It's a little bit idiotic looks initially, but it would really make it easy. Pi's plus Pn over n. So you see, I just wrote this. Oh no, I'm writing right side. So I'm writing this one, and in the argument I split this sum up to n into sum up to n minus 1 and the last term. Okay, so this would be my lambda, and this would be my 1 minus lambda. Okay, good. So now I can guarantee by this inequality that this is larger than n larger or equal n minus 1 over n s that's my first guy. Okay, and now because I'm doing induction, then I'm saying, look, I'm proving on the n steps, but I'm assuming that it's true on n minus 1 steps. So this, which is the sum up to n minus 1, I can definitely say that if I assume that this is true, then this I can replace by 1 over n sum n minus 1 s of pi's. Okay, and plus s of Pn over n, which is 1 over n sum of s of pi's over n. So this is equal to this, and z was equal to z. Okay, this is called Jensen inequality, and it's very technically useful. We'll be using it over and over again. I just decided to work a little bit through all this simple convexity just to let you be very comfortable with convexity. It's a very important property. So let's just at this moment reflect a little bit where we met already convexity. We first met it in thermodynamics, where we say that when we want to come out from entropy as an argument to temperature as an argument, namely we want to make a Legendre transform, instead of argument we want to consider derivative with respect to this argument. This we can only do for convex or concave function. For function whose second derivative never changes sign. So that for every slope it has a different argument, right? That's the first time we get convexity. Second time we get convexity in this very important property of dynamical chaos and entropy growth and volume growth and entropy decay in many ways. But it was basically the statement where we use the convexity of an exponential function of lambda. Yeah? So we use convexity of the exponential function, but saying that whatever you have, if its average is 0, exponent of this average, its mean value is larger than unity, always. Okay? Convexity also, in a purely geometric way, means also that your extremum is reachable. For example, you remember that this S of E, again in thermodynamics, the fact that it's convex, it's not important that whether it's monotonic or not. It's important that it's not like this, right? So that those are states which are possible, right? But if you want to reach the thermal equilibrium, which is the boundary of this area, and you are working at, let's say, constant energy, you go to maximum of entropy at every point, right? And if you are at a constant entropy, then again, you're either going to minimum energy if you're at positive temperature, or you're going to maximal energy if you're at positive temperature, but you always have your boundary to reach. If you would have your domain like this, from here you cannot reach this point, right? So convexity also plays this role, which is again very powerfully used in mathematics, as that your domain is convex, not a function, domain, so that you can reach your boundary just by a straight line. Okay? And now you see that convexity also important because it defines you a very important set of inequalities, which of course physically is very, very natural, because this is the entropy of microcanonical distribution, right? And it's total maximum. But from the informational viewpoint, it tells us the moment we know anything about probability of our letters, DNAs, molecules, prices, our entropy is less. Any any non-uniformity in distribution immediately lowers the entropy. Okay, so that's why it's, in a sense, it's something that we meet over and over again, and sometimes, you know, when I was a student, I had once a kind of a very hard conversation with my instructor in differential equation. He says that you are smart but very lazy. I say, yeah, but smart people are supposed to be lazy. I say, no, I was in the same group as Arnold, and he was always most hardworking. I say, who is Arnold? I was so ignorant. And Arnold is a great mathematician, and he just so happens that Arnold was giving a talk, and he brought me there, and Arnold was really impressed me very much. He was probably 40. Anyway, there he said a sentence which I always remember. He said, physicists, addressing us, say, physicists see analogies between phenomena. Mathematicians see analogies between analogies. Okay, so that I sometimes trying to raise you into this level when I'm not discussing a physical idea, I'm discussing a mathematical idea, which is convexity. It's a mathematical idea. And how you start seeing analogies between analogies, because essentially you're using different analogies in totally different things. Okay? Good. Any question at this point? Because we're about to go to the next section. Questions? Again, let's reiterate. A choice of log n, then we added pi's. We defined entropy as p log p. This minus is mixed here. Then we discussed what is asymptotic equipartition, or a very, very important, a powerful statement that really long strings, messages, sequences are typical, and it means that they inside themselves contain all the information as long as you consider them to be independent. Now, of course, we'll go into what if now we know that they also contain information about something dependent, that some letters, that if you're in English, somehow you notice that after Q, it always U, right? And then you see that there is already some correlation. Questions?
I have a question regarding this equation.
Which one?
From
This one?
No, the second one. From the sum of lone p's.
This one?
No, it's the one on top.
This one is equal to that one.
And that one is equal to the expectation value, right?
Well, this is a statement that the logarithm of probability of the whole sequence is just the sum of logarithms of every symbol in it.
Yes. And you were saying this is equal to the expectation value?
Yeah, what I'm saying is I'm using here the law of large numbers. Okay, thanks for asking, because maybe it's worth repeating here. So I'm using a law of large numbers. This is something which I just read from this particular string. Just how many times P1 happened, how many times B happened, C, D, etc. Now I'm saying, look, it's a very long sequence, which means that this is already exponentially close, exponential in n, okay, close to its mean value. But mean value of a logarithm is entropy. Okay, so what I'm saying is that if you are interested in the sum of logarithms divided by their numbers, okay, for sequence of 5, it's whoever knows what. For 5,000, it's already sum of 5,000 numbers, and you say it is it's with exponent minus 5,000 with that accuracy, it's close to its mean value. But mean value of a logarithm is entropy. Okay. So again, entropy is a mean logarithm. It determines the rate with which total number of sequences grow with the number. That's how we obtain it. We did it. I already erased it. Okay. So the number. Let me really return to it, because this would be the most important. Number of n strings it's 2 in the power n s in bits of p. If those strings made out of independently chosen sequences. Okay? And respectively, the probability of any given string is 2 minus ns. Or in this case, we did it exponentially because we took s in lengths, not in bits. Okay? So this statement that the logarithm of probability approach entropy, which means that the probability is exponent minus n entropy, or which is the same as 2 minus n s entropy in bits. This is a counterpart of the fact that the number of such string grows. But we use this number of such strings when we say what is the information brought by a single string. It's a logarithm of a number of total number of possible strings. Okay? So now probably I would just announce what will start next week, and then we'll start next week because the remaining like 5-6 minutes. We now will do communication theory. Again, like everything that I do, like standing on one foot, in a sense, it's very fast. Engineers would be aghast. That physicists do communication theory like in 1 hour, maybe hour and a half. So in essentially what we'll be asking the following questions. We'll be asking that, okay, this given string of alphabet letters, for example, it brings me that much information. Okay? Could I code it in such a way that I would use a minimal number of symbols? Or another way, what kind of coding I need to use if I want my information be maximal per symbol? Okay? Because generally, of course, I can do it kind of in many different ways. Right? And for example, if I am using alphabet, and I know that which means that for every letter one symbol, and I know that different letters happen with different frequency, that's totally idiotic, right? Because right way is what Morse first started to do, is to choose the most frequent letter and take the shortest code for it, and take the very, very rare letter like Q and code it by 5 symbols, not by 1. And that's what actually Morse did. Morse coded E by a dot, and he coded Q by, I guess, something like this. Okay? Which, because on average, you quite rarely would use this 4-symbol combination, you would gain a lot. But then the question is, what is the maximal rate, or what is the shortest code word? Mean code word, right? So you have different objects. And of course, our cells do it all the time because they decide how actually they encode this amino acid or that amino acid. So next time we solve a model problem, how you would actually build a perfect genetic code for some fictional creature who would really make your rate of information maximal. And again, I'm not afraid to give away user secret. You'll find out that the maximal rate of information transfer is the same Gibbs entropy as the mean rate of information transfer. And then we ask next question, which would be, but if we make errors, what if our communication channel, and at this point we understand that moment we say communication channel means everything. It's what I tell to you, it's what we measure in our lab, it's what we retrieve from memory of our computer. It's all communication. It's all just from here to here. If you record something and then retrieve it from a memory, it's a message sent in time. Okay? Or message could be sent in space. But it could be accompanied by errors. And these errors mean that we actually need to send a little bit more to correct for these errors. We need to send some checks, etc. And there we'll introduce the next most important quantity in this course, which we'll call mutual information. And that's where we start talking about why letters are correlated and why U always follows Q and how to measure this. Okay? So this would be next lecture. It would be communication theory. I hope we'll do it in one lecture, but then we'll be using it in other things. Okay? Good. More questions? Yes.
So we're seeing the analogy to Gibbs entropy, for example, and we have Boltzmann distribution. Is there an analog of temperature here?
Good question. Yes, there is an analog of temperature, but it's very non-intuitive at this point. To get temperature, you need, apart from entropy, you need energy, which means something which is related to something different from your information. And that would be a use for which you are trying to put it in use. Okay? It will be something which is called rate distortion theory or marketing strategy or whatever. The moment that something else appears for which information or entropy is a tool, then you get temperature. There will be a lot of it. But for this, again, you need first law of thermodynamics and second law of thermodynamics. So far, we're only on the law of the level of entropy. There is nothing else. When we start using it, this information, then will appear temperature. Okay? Good, we're done. End of the week. Okay.